Good morning, Honors Algebra 2. We're going to get started with section 8.5, day 2 notes, which is the probability of dependent events. So, dependent events is when one event impacts another. We talked about that just a smidge yesterday or the day before. Now, the probability that B will occur given that A has occurred is called a conditional probability of B given A. And we write this as P of B given, this line means given, A. Now, again, this is when one event impacts another. That's how you write the event for a probability. Now, the probability of dependent events is if you have the probability of A and B. This is equal to the probability of A occurring times the probability of B given A, right? Because again, one event impacts another. So if you have 10 flowers, if you have 10 flowers to choose from, you have 10 over 10 choices. But when you pick a second flower, now there's only 9 flowers left, so you have only 9 flowers to choose from, okay? Now another way you'll see it written sometimes is the probability of the conditional probability is equal to the probability of A and B over the probability of A. Now if you go on in your young lives to take AP statistics or statistics in college, this is what you'll see more often than the other equation. Okay, let's jump into it. So, some examples. We're going to find the probability. Okay, so this first one is not a dependent probability. So, the probability that the listed animal is a reptile. So, this is not a dependent probability. This is the number of reptiles over the total number of animals from our chart. Now, I'm not going to make you count and do some mathy math. The total number of animals is 475. Now, the total number of reptiles is what you're going to, add. You're going to add this column together, 14 plus 21, and that gives us 35 for our top. And when we reduce this, you can either write it as a fraction, which is 7 over 95, or a decimal, which is 0.039. Either of those is fine. Now, part B is going to be a conditional probability. What is the probability that an endangered animal is a reptile? Okay, so that means when we write out a probability, we're still trying to figure out if it's a reptile, but it has to be given the condition that it's endangered. So what that means is, so this is probability of just reptiles. So this is the probability it's a reptile given that it's endangered. So what you're going to need to do is you're going to have to figure out the number of, and let's just do this in a different color, shall we? So that we're not getting confused. And back to it. So it's the number of endangered reptiles that we're looking for over the total number of endangered. I feel like I spelled that wrong. So your top focuses on specifically endangered reptiles, while your new different total is going to be just endangered animals. Now again, I'm not going to make you guys count this out, but the total number of endangered animals, so we'd add this first row together, this would give us 355. And then the total number of endangered reptiles is specifically just 14. Now this would be the fraction, it doesn't reduce, or if you're a decimal person, it would be 0.039. And please note that I changed the the decimal up here. It's supposed to be 0.74. I do not know how to read on my calculator. Okay. Now, looking at number 2, you are randomly selecting 2 cards from a standard deck, and remember, a standard deck has 52 cards. what is the probability that the first card is not a face card, okay, and the second card is a face card? So there are 12 face cards in a deck. Let's just make sure we know that. So the first one, you're replacing the first, so that's important. You replace the first card before selecting the second. So that means I'm picking my first card, putting that back, and then picking my second card. So here we go. Let's write this out. So the probability, not a face card, and then we pick a face card. So this is equal to the probability, not a face card, times the probability it is a face card. There is no conditional probability here where there is no depending on the event prior because we replace that first card. This equals to, now if it's not a face card, that means we have 40 cards out of 52 we can choose from, times, and since we replace it, we have 12 face cards we can choose from out of 52. And when we do the mathy math, we get 30 out of 169, or if you're a decimal person, 0.178. Now let's look at number 2. I'm sorry, number 2. Letter B. You do not replace the first card. So this is a dependent event. Okay, so we get the probability of not choosing a face card and the probability of choosing a face card. But now our probability numbers are going to look different. Okay, this is equal to the probability not a face card times the probability of a face card given that we originally chose not a face card. Okay, so this is going to be a dependent probability because we have a conditional probability. This is dependent upon the first thing we did. So, probability of not choosing a face card the first time is still going to be 40 out of 52. Times, since we do not replace that card, how many cards do we have in our deck? We got 51 cards in our deck, and we still, since we didn't choose a face card, there's still 12 to choose from. Okay, so that's how this one's different. Be careful with wording, be careful with wording. Oh my gosh, be careful with wording. So this is equal to 40 out of 221 if you're a fraction person, or 0.181 if you're a decimal person. So in both of these examples, 1 and 2, A was an independent probability and B was a dependent probability. There's a factor that was important in order for us to find our answer. Okay, let's look at 3. You and 2 friends go to a restaurant because restaurants are now open and order a sandwich. The menu has 10 types of sandwiches and each of you is equally likely to order any type. What is the probability each of you orders a different type? Okay, so this is a case where you're going to have dependent probability. So we're going to have conditionals. I think I spelled dependent wrong. That's okay. So we're trying to figure out the probability of you and a friend, or friend 1, and friend 2. So your probability is what you choose times, now if you're not going to have the same sandwich, now it's the probability of what we're going to just, friend 1 is just going to be 1, or F1, we'll call him F1, friend 1. What friend 1 chooses given the sandwich that you chose, times the probability of what friend 2 chooses given what you and friend 1 chose. So that's how you write out the conditionals here. So there are 10 sandwiches for us to choose from. So when you get to choose, since we're going to let you choose first, you have 10 out of 10 sandwiches you get to choose from. Woohoo! Times. Now, the number of sandwiches in the menu doesn't change for friend 1. So it's still going to be out of 10. But if you chose one of those sandwiches, he's only going to choose out of 9. Now, friend 2, same thing's going to happen. There are still 10 sandwiches for you to choose from, but he doesn't want the same thing as you and friend 1. So that means he has 8 choices to choose from. And when you do the mathy math for this, you get 18 out of 25, or if you are not a fraction person, 0.72. Okay? All right. Now, we're going to use a tree diagram to show dependent probability. This is going to be a little bit long, so if you want to slowly zoom ahead, totally understand. So using a tree diagram, the American Diabetes Association estimates that 5.9% of Americans have diabetes. Now suppose that a medical lab has developed a simple diagnostic test for diabetes that is 98% accurate for people who have the disease and 95% accurate for people who do not have it. If the medical lab gives the test randomly to a selected person, what is the probability that the diagnosis is correct? Okay, so we're going to draw this out. First things first, our first little box is going to be the total population. So I'm going to call this total pop. Not soda pop, population. Now, there are 2 different types of people we're talking about. We're talking about people with diabetes and people without diabetes, okay? So we'll call them A for diabetes, so with diabetes, and population B, which is without diabetes. And I'm abbreviating with and without. Now, we are told that there are 5.9% of Americans who have diabetes. So we're going to write this as a decimal. Okay, so we're told 5.9%, so this is 0.059. So that means the number of people without, or I'm sorry, the percent of people without diabetes is 1 minus this number, which is 0.941. Okay. Now we are told that the diagnostic test is 98% accurate for people who have the disease. So, drawing our tree diagram, we have C, diagnosis, correct. I don't know how to spell diagnosis, so I'm going to write it as diagnose, correct. And then we have event D, which is diagnosis, not correct, for people with diabetes. Now, we're told, again, that it is 98% accurate. So, when they use the test, it's 0.98 for correctness. But for not correctness will be 0.02, or 1 minus 98. Okay, now we got to talk about people without diabetes. Okay, so they have the same C and D. Diagnosed correctly versus diagnosed not correctly. Now again, we are told for people without diabetes that it is 95% accurate. So we got 0.95 for the correctness, which means the not correctness is going to be 1 minus 0.95, which is 0.05. Okay, so our tree diagram is all drawn out. Now we are asked, what is the probability that the diagnosis is correct? Okay, so that means we're trying to figure out the probability of our C value here. Okay, we're trying to figure out our C values that we get. So the probability of C is equal to the probability of event A, people with diabetes, and it was diagnosed correctly. So probability of A and C, plus the probability of event B, people without diabetes, and diagnosed correctly. So B and C. So you have 2 different probabilities you need to focus on here. All right, so these are conditional probabilities. So given that someone has diabetes times the probability that it was diagnosed correctly given they have diabetes. plus the probability of someone not having diabetes times the probability they were diagnosed correctly given they don't have diabetes. So that's how you set this up. Okay, this is a conditional probability. In order for it to be correct for someone with diabetes, it's given that that person has diabetes. To figure out the diagnosis correct for someone without diabetes, you have to have the probability given that it's diagnosed correctly if they do not have diabetes. So we just plug in the numbers here. So the probability of A we're given is 0.059. Probability of C given A is that 98% accuracy, or 0.98, sorry. Plus, probability of someone without diabetes is 0.941 times the probability it's diagnosed correctly, in this case is 95%, so times 0.95. And when you get the math done together, the accuracy of this test is 0.952. All right, here we go. Now we're going to switch up into something called a two-way table. So, I like two-way tables. They're beautiful. 100 students were surveyed about their preference between dogs and cats. 36 boys who prefer dogs and 26 females who prefer cats. There are a total of 56 students who like dogs and 48 males. Assume they prefer either cats or dogs. They don't like both. This is a very strict like and dislike. So we're going to make a two-way table. So here we go. Draw as I draw. All right, so here's our two-way table. On the top, we have boys versus girls. And on the side, we're going to be talking about dogs versus cats. And then these last columns on the bottom and on the right here are totals. So let's just focus on the stuff we know. We know there are 36 boys who prefer dogs, 26 females who prefer cats. There are a total of 56 students who like dogs and 48 males. So let's plug those numbers into our table. Let's pick a color that is orange. So 36 boys who prefer dogs, that's going to go in the dogs boys column or box right here, 36. Okay, then we're told that 26 females prefer cats. So where girls and cats collide is right here in this column, this box, and we put that 26. There are a total of 56 students who like dogs. So the total people who like dogs is 56. That's the total on the right. Then we are told there are 48 males. So that's the total number of boys, which is at the bottom. And now what we're going to do is we're going to do some math to figure out the rest. So if 36 boys like dogs and there's 56 students, that means that 20 girls like dogs. If there are a total of 48 boys, the number of boys that like dogs is 12. And then now we're going to add for the rest of our totals. 20 plus 26, that means 46 girls. There are 46 girls. Number of people who likes cats, 12 plus 26, which is 38. And the totals all together, these two should add to the same thing, which is 70. No. Miss R, learn how to add. 94. Gosh, I hope that's right. It is. Okay. Now, we are asked, what is the probability of females who like dogs? Well, let's look at our chart here. Where are females that like dogs? That's this value right here. Now, probability cannot be a number greater than 1. So, we need to write this as a fraction. So we know 20 goes up top. We're not given a condition, so we have to just do this out of the total number, which is 94. Okay, and this simplifies to 10 out of 47, or if you're a decimal person, 0.21. All right, let's move on. Let's try a next one. So, example 6. I want you guys to just make the table on your own, but we're going to read it through together. A survey is conducted of 50 people about who likes coffee and who likes tea. It is found that 20 people like both, 15 people like coffee but not tea, and 10 people like tea but not coffee. All right, so try and make the table on your own. See if you got this. Okay, hopefully you got this as your table. So you had a two-way table. It was either they like coffee or not, and then if they like tea or not. Now, the survey conducted with 50 people, so 50 is your total down here. 20 people like both, so 20 people who like coffee and tea. There's 15 people who like coffee but not tea, so coffee but not tea. And then 10 people who like tea but not coffee. So I wrote that value in. Now, if you did coffee on the sides here and then tea on the top, don't worry about it as long as your values kind of match up. So the total number of coffee people is 35. No tea or coffee, they don't like either, is 5 people. The total number of people who don't like coffee is 15. The total number of people who don't like tea is 20. The total number of people who do like tea is 30. All right, so let's figure out the probabilities. So, probability of people who like tea. So this is only focusing on tea. So, if they like tea, we have, let's see, where are they at? So, number of people who like tea is 30. There's 30 people who like tea, and it's 30 out of 50. We're not given a condition. So this is 3 out of 5. Or, again, if you're a decimal person, that's going to be 0.6. All right, people who like coffee and tea. Who like coffee and tea? Well, that's this 20 value here. So this is equal to 20 over the total number of people is 50, which is 2 out of 5, or if you're a decimal, 0.4. Then we're asked people who like coffee or tea. Oh, bringing back some old skills here. So that means we have to take the probability of people who like coffee, we'll start with tea. Probability of people who like tea plus the probability of people who like coffee. Now, here's the thing. We have people who like just coffee, we have people who have just tea, but we also have people who like both. So we have to subtract the probability of people who like both tea and coffee. So, probability of people who just like tea is 30 out of 50, plus the probability of people who like coffee is 35 out of 50, minus the people who like both, which is 20 out of 50. And this gives us 45 out of 50, or 9 out of 10. And if you're a decimal person, that's 0.9. Now I'm going to show you a dependent probability based on this table, okay? Okay, now some conditional probabilities. So for letter E, I want you to write the probability given they're a coffee drinker, but they don't drink tea. Now, given they're a coffee drinker, that means this is going to be the bottom of our total. Okay, so the total number of coffee drinkers is 35, so that's the bottom of our total. But they don't drink tea, well, that's coffee but not tea, which in this case is the 15, so that's what goes up top. And this reduces to 3 over 7, and I don't have the decimal in front of me, so you'll have to do it on your own, sorry. Now, we have for letter F, the probability that given that they don't drink coffee, nor do they drink tea. So our coffee is the bottom of our fraction. So the people that don't drink coffee in this case, that's a total of 15. And then the people who don't drink coffee nor tea, well, that's 5. So we have 5 over 15. Well, that's 1/3. Or a decimal, which is 0.33. Okay, so that's how you do it with dependent probabilities in a two-way table. Okay, I hope you guys have a wonderful day. Until next time.